Often taught with introduced with linear equations or functions are the concept of scatter plots. And a scatter plot is a graph of ordered pairs of numerical data. And what we want to do is we want to use linear models to approximate data and make predictions and determine the reasonableness of a model of a given and the goodness of it. So the goodness of it, that is the accuracy of it. And what will tell us the accuracy of a model is the correlation coefficient. And that will tell us percentage-wise, it's up to a 100% accuracy, and then it varies from there on. For example, as we were graphing a linear equation, when I would graph a linear equation, that's a straight line. That is the goodness of that is 100% because it is a straight line point for point. However, scatter plots we're going to find may not have that same appearance of a straight line. The data may be a little bit spread out, but I think we'll be able to tell what kind of relationship we have as we progress through this. So looking at this, a scatter plot, as I said, of course, is a graph of ordered pairs of numerical data. And then interpolation is the process of using the data and identifying information within our data. And we'll go over an example of that. I already talked about the correlation coefficient. Extrapolation. So if I have a graph and I have a series of data, I'm going to make a determination using interpolation right here of the information that may fall within my graph. That's interpolation because it's within my data. Extrapolation, on the other hand, may occur out here outside the scope of my data, but I'm making a prediction or an estimate on some of the information as I determine it. A line of best fit is when you have a linear function that best represents the given data. So if I were to look at those points that I just put here, I might say that a good line of best fit is that line right there because it sort of splits my information. I have some of my data up top, some of my data below. It seems to be going in that. I'm following along with my data. So that would be me predicting a line of best fit. The correlation is much like a slope, where as we look at this relation of the example that I just put up here, my data seems to be moving in a upward positive direction, so that would be a positive relation. We'll cover into more of that. And then, of course, my linear regression is what we do is the method of finding the equation of line of best fit for the data set, and the calculator is going to do that for us, thankfully. And we'll learn that process as we go. So with that, so we have, when it comes to relation, we have three main types of relationship. We're going to have what would be considered a positive relationship, a negative relation, and then no relation. I'm looking at these graphs, and if we think of the positive, the negative, and no relation as a slope, if we were to look at the information and data, as you can see, these points are not in a direct straight line of a linear function, but it seems to be that they're close, and they're heading in some direction. As my x-axis is increasing, so is my y-axis. And just envision that if I were drawing a line along that, what kind of slope would that line have? And I'm hoping that you're going to tell me that that would be a positive slope. Therefore, we have a positive relation. The same thing goes for this next one. If I draw a line along my data, it seems to be going in a negative. As my x is increasing, my y is decreasing. So that is giving me this negative effect. Much like stepping on the brake. The more I step on the brake, the slower my car goes. That's a negative relationship. versus the more I step on my gas pedal, the faster I go, and that would be a positive relationship. Um, looking at this last one, I really can't tell. I can't tell if I'm moving up. I can't tell if I'm moving down. I mean, it could be going this way. I don't know. So that falls under unsure. And if you can't tell if it's positive or negative, it's a no. Okay? It's no relation. No relation. So that's just looking at the points and just sort of trying to see how are they traveling. And basically we have a positive pattern, a negative pattern, and no pattern. So those are my relations. And when we talk about the correlation coefficient, that actually means the data, how fast or how tight and close the information is. If I take this, for example, and if I erase this junk, and I could say that this is a fairly accurate piece of data right here. All the information is close, but however, if I were to add a couple of points in there, all of a sudden my data is going to expand out and my data is spread over a larger area. It may still seem to be in a positive direction, but it's a weaker relationship because in essence, my answers are scattered more than when they were tight together. So that becomes a weaker relationship. So that's why this over here has become such a weak relationship. We can't identify the relationship, and that's why it's called no relationship. Okay, so using some of that information that we just talked about, I'm going to say this example. The line of best fit for the scatter plot passes through which pair of lines? Okay, now, if you can't see the relationship here, what we're going to do is we're going to try and draw a line of best fit, and when we do that, what we're doing is we're trying to find a line which sort of splits your information. A little bit above, a little bit below, and it's going in the general direction of the data. So if I were to take the segment of P and Q and I were to connect them right here, P and Q. Well, if I look at that just from a sharing of, how did I disperse the data? Well, there's very little up top, but on the bottom there's a lot more information. So I didn't split my data evenly here, okay? So I definitely want to exclude that because that is not a good line of best fit. It doesn't split my data as even as possible going in the right direction. Now, if I look at P and T, if I split my data here, well, it seems as if I have a little bit above and a little bit below. However, the inequity of it, if you'll notice, when I talk about the data that is above my line, it's all to the top right, and then the data that is below my line is focusing on the bottom left. So that is not very evenly distributed along the entire length of my line of best fit. So let's look at another option, and I guess what I can do is I can leave that last one up there too. This is the last one that we drew. Looking at RQ, we'll draw that one in blue. RQ is right here. All right, and I would say that that doesn't look too bad. It looks like it's following the data. I do have a few above and a few below, so that's a possibility. And then if we plug in one more here, the SQ and SQ right here. Okay, I would definitely say SQ is not going to be a possibility. Okay, let's cross that one out. And then the other ones we just have to look at and say which one seems to follow the data better, and I'm going to go with RQ. RQ seems to follow the information a little bit better than the other lines. So we have point R, point Q, a little bit above, a little bit below, and it seems, the data is evenly dispersed. So that would be drawing in my line of best fit. Now we're going to use that in this next step where it says, Joe plotted the number of participants in the summer camp program on a coordinate plane to create the following scatter plot. Okay, so there's my scatter plot. Look at our data. Number of participants and the year since 2000. Well, that's the big important thing. Year since 2000, right? So this would be 2010 probably, 2020. So we're going by years there. So we didn't just start at the origin. We started at year 2000, and participants would be 0. Looking at that, and then we have the number of participants, and they're going up by 10 over here. And to look at this, what we know about data, the relationship, hopefully you can see that as my data seems to be increasing, as my participants are increasing, as my time is increasing, my participants are increasing. So it looks to me like we have a positive relation. So we call that a positive relation. Positive relation. And if I were to draw in my line of best fit, if I were to split the data, I think I could probably do, I don't know, if we just estimate, right? It's an estimate, make an estimate right there. So one point I have that if you'll notice right here in year 2000, I had 40 participants. So I could create an ordered pair out of that. Not that I have to, but I'm just going to. In year 2000, or at my starting point of 0, I had 40 participants. And then it looks like what's my slope? And if I want to find another point, then if I want to find my slope, and I could say that this point right here might be the equivalent of, we could just estimate and call it 75. Right here. And we'll call that 75. And then if we went down here, that would probably be 11. Okay, so that ordered pair, I could say, is going to be X is 11 and my Y is going to be 75. So I have found 2 points along my line of best fit where I can now turn around and I'm going to create an equation of a line. And this is adding to the information. So in order to create an equation of a line, I'm going to create an equation using my slope-intercept form. Y equals mx plus b. And I will tell you that we already have b. B is going to be 0, 40. That is my y-intercept, and this point right here is my y-intercept. So I know that I already have mx plus 40, because 40 is going to be the starting number of participants I have. But I do need to find out what the heck is m, and hopefully you remember that we can determine m by using y2 minus y1 over x2 minus x1. And we have those x and y values right here that we can use. So my slope is going to be equal to 75 minus 40 over 11 minus 0, which is going to give me 35 over 11. Now I'm just going to leave that as the slope, and I'm going to leave it as a fraction. So if I do some substitution right here, in order to create a line of best fit, and I've done it graphically and algebraically, I have y is going to be equal to 35 over 11x plus 40. There are more accurate ways to do this in the calculator, but that was just some stuff that I was able to come up real quick. For example, on a test, any answers they gave me that had a slope that was negative, I should be able to look at this and say the relationship is positive, my slope is going to be positive. So there's little characteristics like that. I should be able to look at the equation of a line and say, you know what, my y-intercept is going to be approximately 40. If they gave me an answer that said my y-intercept was 120, that's nowhere near my data. That's definitely not right. Or if they said it was going to be 10, 10's not right either, because that's nowhere near my data. So just being able to look at a line of best fit, putting the line in there and looking at my data give you a lot of the information you need to know. So that's using scatter plots to help us come up with information. And again, this is a bit of a review. Definitely covered this in algebra, not so much in geometry, but it's just, looking at those things and identifying those characteristics, and just by knowing the definition and the words will help eliminate a lot of the stuff out there causing you problems.